Hey guys, I hope you are doing well. My name is Amir Hossein Farzadi, and in this video, I want to talk about a command in optimization toolbox in MATLAB. Actually, the problem is how can we solve a linear programming problem in MATLAB? As you know, there are many ways for solving this type of problems. However, these ways maybe take many times. Solving the linear problems are the basic concepts of operations research. In addition, linear programming is the most important method for, optimizing the linear problems. Although there are many softwares for optimization, like GAMS, Lingo, Lindo, Excel, and so on, but programming languages have a key role for solving optimization problems. So if you want to get better results and options after the optimization process, you should use better ways. Actually, in programming, not only you are not bounded for defining a problem, but also you can customize the syntaxes. Python and MATLAB are the popular programming ways for optimizing. You can import some libraries before initializing your problem in Python or use some commands for solving an optimization problem in MATLAB. In my experience, MATLAB has better performance for solving the optimization problems. You should just define the parameters as inputs for the relevant command. For the linear programming problems, we have a really strong and easy command which is called linprog. Actually, it finds the minimum of a problem specified by the last box rule. Based on our needs, we can call it in 6 different ways or syntaxes. So as you can see here, in the first 3 syntaxes, we just have one output, which is called X. However, you can define the outputs in all syntaxes whatever you want. For example, M, N, P, S, and so on. And after that, in the last 3 syntaxes, we have at most 5 outputs. You may ask yourself why a function can take more than 1 output, despite the fact that we learned in math classes in the past, a function must have just 1 output. Actually, the functions in MATLAB are not bounded. You can define many outputs for your functions. Here is a linear optimization problem that has one objective function which is called z and unequal or equal constraints. The general objective function notation is sigma I equal 1 to n fi times xi, or the vector notation is, f transpose times x. And what are x and f? X is our decision variable and f is the coefficient of x. And after that, for the constraints, we have inequality or equality constraints. Actually, A is matrix that consists of the coefficients of each decision variable in each constraints, and B is our resources, actually the right-hand side numbers. Okay, so we have also another constraint in that for the decision variables, we can define lower and upper bound. So let's solving a real problem. You can see here an objective function subject to 3 inequality constraints. For solving this problem with linprog command, we should provide or exploit f, a, b, a equal, b equal, lower bound, and upper bound from our problem. In the previous slide, we defined f as coefficient of the decision variables in objective function. So for the stage 1, we should exploit the f. And here you can see -5, -4, and -6 as the coefficients of the x1, x2, and x3. So for exploring F, we should convert F transpose to a column matrix. In the second stage, we should exploit A and B from our constraints. As you can see here, we have a matrix which is called A that consists of the coefficients from each variable in each constraints. To put it more simply, in the first constraint, you see 1 times x1 minus 1 times x2, and after that, 1 times x3. Well, so in the first row of the matrix A, we should write 1 minus 1 and 1, as you can see here. And we will continue to do so until the end of these constraints. For example, in second constraint, we have 2, 3, and 4, and also in the second row of the matrix A, you can see the coefficients are written. And after exploring A, we should exploit B, and as you can see here, the matrix B just consists of 20, 42, and 30. Actually, a column matrix. And finally, we should exploit lower bound and upper bound from the decision variables constraints. As you can see here, all the decision variables are bigger than the 0. So lower bound for all of them are equal to 0. So you should define each lower bound for each decision variable as a column matrix, as you can see here. An upper bound will be defined as default in infinite. But suppose that we have an upper bound like 2. Actually, all the decision variables are smaller than 2. So we should define upper bound for each decision variable as well. Okay, so far we have been able to exploit F, A, B, lower bound and upper bound. But for the A equal and B equal, we did not have equal constraints. So we should equal them to the empty brackets, okay? So let's get started programming in MATLAB, and after that, solve this linear problem. For time managing, I coded this problem before, so I explain line to line of this code. As you remember, we exploit the inputs of this command, actually F, A, B, lower bound, and upper bound. So we should just define them for MATLAB. So as you remember, we convert F transpose, which was row matrix, to F, which was column matrix. So here in MATLAB, we should define the F as a column matrix. So as you can see here, -5, -4, and -6 are separated by semicolon. Actually, you can use this sign for making a column matrix, or you can also click Enter key in each number after the first number to the next line. As you can see here. And for A and B, we define the values as the same of F. And after that, A equal, B equal, and upper bound are equal to empty brackets. Okay, so far we defined all the main inputs, and now we should just call linprog command for solving the problem. But let me opening the documentation of this command. As you can see here, the syntaxes are defined, and also you can see some examples and more informations. Each output that mentioned in MATLAB here actually just give you more informations about the solving process. But this syntax is the main syntax that need for getting the value of objective function. So let's run the problem by linprog. Okay. So as you can see in workspace window, the function value is -78 and the decision variable are written here, or you can call it in command window. Okay, you can see the value of each decision variable. Thanks for watching.